of the session today, well, I will be presenting some information backed up with quite a lot of field photos on, well, early Earth surface processes as they are recorded to a large extent in the Southern African context, and we will see quite a lot of photos that relate to the Southern African geological record. Obviously, if we would like to investigate surface processes on the early Earth, we are interested in looking at sedimentary rocks, also volcanic rocks, basically supracrustal rocks that can tell us something about the conditions on the Earth's surface in the far distant past. And over the last 30, 40, 50 years, study of these kind of rocks have provided us with quite a lot of clues on, well, the type of conditions that were present on the early Earth. And here are a number of conditions that are listed here that are characteristic for early Earth. So we are all fully aware that there was much higher concentrations of greenhouse gases in the early atmosphere at the time, mainly CO2, but also CH4 to some extent. In contrast, the oxygen concentration in the atmosphere was very low, and as a result of this, there was no ozone shield present at that time. There was a magnetic field present, but it probably was to some extent weaker than today, but it was sufficiently strong in order to protect the Earth from the solar wind. We did have a higher meteorite flux. There was more intense chemical weathering going on the Earth's surfaces at that time. On the seafloor, there was quite a vigorous hydrothermal activity present, and associated with this hydrothermal activity, there was also quite widespread microbial life. And I will show you some of the record from a South African perspective that focuses on some of these surface conditions in the Paleoarchean specifically. So now, if you would want to investigate these processes, you need to have very well preserved Archaean rocks, and well, there are quite a number of Archaean cratons scattered all over the world, but there are only a few places where you can find volcano sedimentary rocks of sufficiently low metamorphic grade. So here we're talking about green schist facies metamorphic grade, and there are not that many places around. The Kapvar craton is one of these places, the Pilbara craton, another of these places, but there are also a number of places in India that haven't really been studied to a sufficiently large extent that do contain well-preserved rocks. Of course, we know that the oldest rocks are to be found in places like here, Isua, but here we're not dealing with green schist facies grade rocks. We have amphibolites, and it's much more difficult to obtain information on surface processes from these highly metamorphosed rocks. Here, a geological map of southern Africa, and there are two areas where you can study Archaean geology. There's a Zimbabwe craton as well as the Kapvar craton. Now the Zimbabwe craton contains quite a large amount of well-preserved greenstones, but unfortunately they are somewhat too young for us. They are mainly of Neo-Archean age. So we will be focusing now on the Archaean geology of the Kapvar craton, and this is the outline of the Kapvar craton, and whatever is shown in color are rocks made of being of Archaean age, and the oldest rocks are those shown in red and black. These are Paleoarchean granitoids and greenstones. The reds are granitoids, the black are greenstone belts, and I will be showing you some information from some of the oldest greenstone belts. Many people know very well the Barberton greenstone belt, but there are quite a number of other greenstone belts further to the south that are just as well preserved as the rocks in Barberton, And one example is the non-veiny greenstone belt in the southeastern part of the crater. So you have seen this image before, this nice view of the lower part of the Onverwacht group, volcano sedimentary rocks that range in age from 3.5 to around 3.3. These rocks are very well preserved. They are basically steeply dipping, almost vertical, and here you have the oldest rocks, and if you would walk in this direction, you would walk across successively younger rocks. So you have layers by layers of volcanic as well as sedimentary rocks, mainly pillow lavas and komadiites, but also the odd sedimentary rock that tells you something about surface processes at that time. If we would be moving in this area into these mountains that are underlain by the Huchenhof Formation, we would be able to see this kind of scenery. Again, we have predominantly volcanic rocks forming a pile that is basically steeply dipping, forming this layer cake stratigraphy. And in between the various volcanic rocks, you find thin sedimentary horizons. And I depicted them in this image. They are made of chert. They are a few meters thick. Typically, you can trace them laterally for many tens of kilometers. And well, right at the top, there is probably one of the thickest chert units that is known to exist in the Archaean. That's the Buckreef chert, which I will be talking a bit more about. Now, these cherts are probably the best record for surface processes in the Paleoarchaean. These cherts come in different varieties. A very common kind of variety is a banded rock, banded black and white chert, which contains quite a bit of organic matter that forms black coloration. These are relatively deep water deposits. We find much more shallow water sedimentary units, which show lots of evidence for wave activity and currents. You see cross-bedding preserved in this rock, indicating, well, that this is not a chemical precipitate, but it consisted out of sand-sized particles that were moved around on the very ancient seafloor. If you look carefully at these rocks under the microscope, you find that they contain quite a number of different components and can provide quite a lot of information on the conditions in which these rocks formed. Many cherts contain various fragments that are organic rich. Some of them, they consist of ripped up microbial mats and quite a number of other organic rich components that formed predominantly in a shallow water environment. Now, some of these cherts, they contain grains that clearly indicate volcanic activity, accretional lapilli, volcanic glass shards that are preserved in these rocks. The preservation is exceptional in these rocks because they got silicified very early, and this is why they show a large amount of chert cement in between these well-preserved grains. Sometimes you come across spherical grains that formed due to meteorite impact, and there's quite a number of interesting horizons of these impact spherolayers preserved in the Barberton Greenstone Belt. And if you're very patient, you may also find filamentous forms made of carbonaceous matter, and these are potential microfossils that you can come across after spending maybe sufficient time looking at maybe tens or hundreds of thin sections. Now, this is quite a famous chert, the Buckreef chert. It's probably the thickest chert horizon that is known to exist from the Archaean. Again, we have various layers of different kinds of chert. They are more or less vertically dipping, and these cherts were deposited on some felsic volcanic substrate, representing some sort of volcanic platform that was slowly subsiding. And on top of this platform, you had deposition of these chert units, reaching a thickness of up to 400 meters. The time of deposition was at around 3.4 billion years ago. And a few years ago, we were able to do some research drilling through this thick chert horizon. We obtained a core 900 meters in length, which to a large extent consists of chert. I just show you a few sort of snippets of the ongoing research that is taking place on the Buck Reef chert. Here you see some core trace from the Buck Reef chert. This is core which was obtained right from the bottom of the chert unit. You have in white, that's more or less pure chert precipitate intercalated with more darker bands. Over here, this is chert which is very rich in organic carbon. There are some grayish domains. You have got quite a bit of siderite. If you move higher up in the stratigraphy, like here, this core tray, that shows actually banded iron formation. And here you have chert layers in white, and in between, the gray layers are predominantly made out of siderite, so an iron carbonate that forms this banded iron formation. You also see some little jasper horizons here and there. If you look at rocks here in the lower part, well, this is sort of what you see. These are photos of drill core. We have these very disrupted fabrics of chert fragments floating in some sort of ground mass of what we now refer to as granular chert, sand-sized grains that consist to a large extent of silicified carbonaceous matter. Some of it represents likely some ripped up microbial mats, but much of this sandy material at the moment we are not quite sure exactly in what kind of environment it formed. You see there's lots of evidence for fluid movement, soft sediment deformation, and there is probably to some extent a hydrothermal fluid component that was able to mix and disturb these rocks as we see them here now on the drill core. Another not very common sedimentary facies is a carbonaceous chert, which forms these 10 to 20 centimeter thick units. These chert are quite rich in organic carbon. Sometimes you reach total organic carbon contents of 7–8–8%. Also, these rocks are quite rich in phyllosilicates, chloride, so they represent the equivalent of a black organic rich shale. Much of the clastic material was likely wind derived, and there's this interesting relationship between siliciclastic detritus, as recorded in the increasing aluminum content, and the total organic carbon content, suggesting that whenever you had input of this clastic material in this ocean from which these rocks eventually precipitated, you had input of nutrients, and the result of this increased activity in the organisms at that time that were able to become preserved in the form of the carbonaceous matter. Besides carbonaceous matter, you also find quite a bit of pyrite, which formed during early diagenesis in these rocks. And for example, if you look at the sulfur isotopic composition of this pyrite, you see a large spread in the delta 34 sulfur isotope ratio, suggesting in this case microbial sulfate reduction that gave rise to the formation of these pyrite nodules very early in the sedimentary history of these rocks. We did some chemostratigraphy, so this is basically the drill core. All of this are different facies of chert. Here we have banded iron formation, and here we plot zirconium concentration as a proxy for the amount of clastic material that was brought into the sedimentary environment. You see very low clastic input except for those carbonaceous chert layers that are rich in organic matter. Also at the top where we have got some carbonaceous shales. Here, carbon isotopic composition varies between -40 to -30 with somewhat lighter values present in the lower part of this core. There were probably different kinds of microbial processes operating that fixed CO2 in different manner. Here we also investigated molybdenum isotopes, in this case from whole rock samples. Molybdenum isotopes you can use as a proxy to say something about redox processes, potential oxygen present in the environment at the time. All our samples plot in this gray field, which is a field which reflects modern-day igneous rocks, so there is no clear evidence for any oxygenated conditions at the time these rocks formed. We also looked at iron isotopes, besides quite a number of other isotopic systems, to say something about the processes that led to siderite iron carbonate precipitation. But as I said, yeah, all of this is still ongoing work, and hopefully in 1 or 2 years we can be a bit more definite about this. Back to the field. Well, here this is a buck reef chert which is underlain by this by rhyolitic, felsic volcanic rocks, and at the base of this chert, actually at the base of every chert that you come across in the Paleoarchean record, you have silicification. You have an increase in the amount of silicification of the rocks as you approach the overlying chert. Here's another example of a chert horizon. It's vertically dipping and it's underlain by pillow lavas. Now the pillow lavas, maybe 50 meters below the chert, are well preserved. Here's some example of these. But as you approach the capping chert, you find that these rocks get more and more strongly altered. They get silicified to a large extent. And well, here we have the capping chert over here that is underlain by, well, volcanic rock, which is extremely strongly silicified. It's almost a chert now. This silicified rock is cut by veins of carbonaceous chert, and as you move deeper down, well, you get into these pillow lavas which are silicified, but importantly also there is quite a bit of carbonate that precipitated in the interstices of the pillows, typically at specific levels below the paleo seafloor. So these processes operated during deposition of the chert. These are very early seafloor alteration processes that affected these rocks. A few years ago we came up with a little model trying to explain these processes that are very characteristic for the Paleoarchean record. You don't really find it in the Neo-Archean record only, but whenever you go to places like Barberton, to the Pilbara, to India, also to Isua, you see this very strong imprint of silicification. So you had these low temperature hydrothermal processes operating on the seafloor. At the same time you had deposition of sediment. The sediment contained a volcanic component. The sediment also contained some organic component, which we are still not quite sure where exactly it formed. Did it form in the shallow part of the ocean and settle down? Did some of it form on the surface of the ocean, maybe aided by hydrothermal processes? We don't really know yet. Now these sediments, they became silicified, they became lithified over time, but these hydrothermal processes were still ongoing, and this then gave rise to the formation of hydrothermal fractures that were infilled with carbonaceous sediment, and this is what we see in the form of chert veins cutting through the igneous rocks. These processes are actually quite important for the chemistry of the oceans at the time. A large amount of a variety of elements were leached out of the ocean due to these processes. For example, iron was extremely strongly taken away from these igneous rocks, ended up, of course, in the ocean and eventually in iron formations that you find associated with chert horizons. Also, nickel has been removed during these alteration processes, and some of you may be aware that Archaean sedimentary rocks, shales, are very rich in nickel. And this is one of the sources for nickel, this kind of alteration process. Now, as I said, below these chert horizons, you frequently find veins of carbonaceous chert cutting through these igneous rocks, and these veins typically contain carbonaceous matter, and if you look very carefully, you may come across some filamentous objects of carbonaceous matter, and if you look at them more carefully, you find that they show some segmentation, and they may represent, well, microbes that did live in these hydrothermal systems. So, in conclusion for the Paleoarchean, well, we did have processes that were somewhat very different to processes that operated later in the geological record. Lots of silicification, chert deposition, widespread microbial activity associated with these hydrothermal processes. We hope to gain some more information on our work that is in progress on the Buckreef chert. Quickly now moving to the Witwatersrand, the Dominion Pongola Witwatersrand Basin, which is a continental cover succession that sits unconformably on these much older rocks. Here you see an example of the unconformity. Here we have some older granite overlain by this sandstone, overlain by basaltic succession. These are intracontinental volcano-sedimentary successions, beautifully preserved in places. So the green, these are volcanic rocks. The yellow, these are sandstones. Here you see them quite nicely in the field, extremely well preserved. Many of these rocks, the sedimentary rocks specifically, they show evidence for deposition in relatively shallow water subjected to tidal activity, with shallowing upward cycles very prominent. So these shallowing upward cycles have been used for stratigraphic subdivision. So this is the same that what you do in much younger sedimentary basins, subdividing the record on the basis of their sequence stratigraphic record. One thing that is somewhat different to the younger successions is the abundance of pyrite. So this is detrital pyrite that is, of course, more or less absent in rocks younger than the great oxidation event. Pyrite, which is unstable under oxygen-rich conditions. This pyrite is to a large extent associated with gold, and here you have got some concentrically laminated pyrite that in places contains quite large enrichment in gold, and we think that these kind of pyrites were also produced by microbial processes, and in the end it was these microbial processes that gave rise to enrichment of gold in, well, the Witwatersrand Basin, which is the world's largest gold field, and this is also, of course, why South was a prominent player in the mining activity of gold in the past. Very interesting units, sedimentary horizons, that tell you quite a bit about Mesoarchean surface processes. I'm running out of time here, but paleosols play a prominent role in the evaluation of surface processes. We do find evidence, the first evidence for oxygen-rich conditions preserved in banded iron formations of the Mosin group, as recorded by a large fractionation of molybdenum isotopes. So here we had the first whiff of oxygen recorded in the Pongola supergroup, and well, the origin for this oxygen, well, can be found in, well, stromatolites that are quite well preserved in places of the Pongola supergroup. And, well, besides these stromatolites, you also find quite well preserved microstructures, like in the form of these carbonate ooids that are rich in carbonaceous matter, and the carbonaceous matter is associated with a number of biophilic elements, as indicated by this nanosims analysis that shows that microbial processes were responsible for the formation of these ooids. And in conclusion now for the Mesoarchean, well, things look very similar, or much more similar to the modern day volcanosedimentary processes that operated at that time, left a very similar sedimentary record to much younger rocks. We had abundant microbial life in shallow water deposits, and at that time also the first whiffs of oxygen that was a result of well, the activity of cyanobacteria at that time. So with this, I'd like to acknowledge a number of people here, and thank you for the thank you, audience. Please, if you are interested in any of this kind of material, there is core available at the University of Johannesburg from, for example, the Barberton Drilling Project that is available for further study. Thank you.